everyone, and welcome to topic 7, Modern Convolutional Neural Network. So far in this lecture, we have learned different components of CNN, different layers, and different variants of the CNN. In this lecture, we will put everything together and stack this layer and build one network architecture. Specifically, in this video, we are going to learn LANet architecture proposed in 1989 and then AlexNet introduced by Alex Kirsovsky in 2012, followed by VGG network and also networking network, which introduced in 2013. LANet introduced in the research paper with the title of Gradient-Based Learning Applied to Document Recognition. They use this architecture for recognizing the handwritten and machine-printed characters. This paper also introduced the MNIST dataset as well. The main reason behind the popularity of this model is, first of all, it is a simple and also a straightforward architecture. Let's understand the architecture of LANet. As depicted in this figure, the Leonard architecture consists of two sets of convolutions and also average pooling layer, followed by a flattening convolutional layer, then two fully connected layers, and finally the softmax classifier. In the first layer, the input for the LANet is like a 32 in 32 grayscale image, which passes through the first convolutional layer with 6 feature map or filter with a size of 5 in 5 and a stride of 1. Therefore, the dimension change from 32 32 in 1 to 28 28 and 6 times. Then in second layer, it applies the average pooling layer or subsampling layer with a size of 2 in 2 and a stride of 2, which result the dimension will be reduced to 6 times 14 in 14. Next, as you can see here, there is a second convolutional layer with 16 feature maps having a size of 5 in 5 and a stride of 1. In this layer, only 10 out of 16 feature map are connected to 6 feature map of the previous layer as shown here. And the main reason for this subsampling is to break the symmetry in the network and keeps the number of connections within reasonable bound. That's why the number of the training parameter in LANet is one of the earliest convolutional neural networks and promoted the development of deep learning. In 1989, Young et al. First applied the backpropagation algorithm to practice application, and they believed that the ability to learn network could be enhanced by providing constraints from the task domain. He combined a convolutional neural network trained by backpropagation algorithm to read handwritten numbers and successfully applied it in identifying and classifying handwritten zip code number provided by US Postal. In these layers are 1516 instead of 2400, and similarly the number of connections are like around 150k instead of 240k. The fourth layer, or S4, is again average pooling with a filter size of 2 in 2 and a stride of 2. This layer is the same as the second layer, S2, except it has a 16 feature map, so the output will be reduced this time to 16 times 5 in 5. The fifth layer, or C5, as you can see here, is fully connected convolutional layer with 120 feature maps, where each of them has a size of 1 in 1. The sixth layer is also a fully connected layer, F6, with 84 units. And finally, there is a fully connected softmax layer with 10 possible values corresponding to the digits from 0 to 9. Back to the 1989, complexity and depth of the network was mainly restricted by limited computational power at that time. And because of this reason, the network did not use at that time. The next network is AlexNet, which introduced by Alex Kirsovsky, a student of Jeffrey Hinton, and the paper accepted by Neurips 2012 with the title of ImageNet Classification with Deep Convolutional Neural Networks. The AlexNet architecture composed of 8-layer CNNs, and they won ImageNet's large-scale visual recognition challenge in 2012 with a large margin compared to other competitors. The network is trained parallel using two small GPU, and at that time they used the two streams of convolution which are partially interconnected. The network of the AlexNet and LeNet, they are very similar from the component wise, but there are also significant differences. For example, first of all, AlexNet is deeper compared to the LeNet, and it consists 8 layers. Of the where we have 5 convolutional layer, 2 fully connected layer, and also one like a output at the end. Another thing is AlexNet used the ReLU activation function instead of the sigmoid, which was really helpful for like increasing the performance. In this figure, we can see the comparison between the LeNet and AlexNet. The AlexNet architecture takes the colorful ImageNet with a size of 224 in 224, and in the first layer, the convolution window with the shape of 11 in 11 is used. Like compared to Linux architecture where they used in the in the first layer 5 in 5 filter size, they used 11 in 11 because most of images in ImageNet are more than 10 times higher and wider than MNIST dataset. Therefore, objects in ImageNet data tend to occupy more pixels, and a large convolutional window is needed to capture these objects. Like the convolutional window shape in the second layer is reduced to 5 in 5 and followed by 3 by 3. In addition, after the first, second, and fifth convolutional layers, the network adds a maximum pooling layer. You can see after the last max pooling layer, we have the first fully connected layer with 4096 output. These two huge fully connected layers produce the model parameters around 1 gigabyte. Due to limited memory in early GPUs, the original AlexNet used a dual stream data design. So where each of their two GPUs could be responsible for storing and computing only half of the model. And at the end, we have like a fully connected layer as an output with a 1000 class, which is like a 1000 class that we have for ImageNet dataset. While AlexNet offers empirical evidence that CNN can achieve good results, but it didn't provide a general template to guide the researcher in designing a new neural architectures. And the design of the neural architectures has grown progressively to more abstract, with a researcher moving from thinking in terms of the individual neuron to whole layer and also block with the repeating pattern of the layers. And the pioneer work is VGG. The VGG introduced by a researcher from Visual Geometry Group of Oxford University, and in a paper with the title of Very Deep Convolutional Neural Network for Large-Scale Image Recognition. The VGG network composed of the several VGG blocks. The basic building block of classic CNN is a sequence of the following. First, a convolutional layer with padding to maintain the resolution. Second, a nonlinearity such as ReLU activation function. And third, a pooling layer such as max pooling. One BGG block consists of a sequence of convolutional layer followed by max pooling for a spatial downsampling. As you can see in this figure, the Bella composed of the convolution with a kernel size of 3, padding of 1, and max pooling of 2 with a stride of 2. The use of Bella leads to very compact representation of the network definition, and also it allows for efficient design of complex networks. The VGG network is a deeper variant of AlexNet, but with main difference. Here, the network composed of the several VGG blocks. This different version of VGG, such as VGG 11, VGG 16, and VGG 19. For example, VGG 11 constructs a network using reusable convolutional block, and different VGG model can be defined by different the number of convolutional layer and also output channel in each block. And in VGG paper, they found that the several layers of deep with a narrow convolution, for example, 3 in 3, is more effective than the fewer convolution or wider convolutions. And as depicted in this figure, we can see the comparison of the AlexNet and VGG network and also like VGG block itself. The networking network introduced in 2013 by Lin et al. And the title of paper is Networking Network. So far we have discussed LeNet, AlexNet, and VGG all share a common design pattern. They extract feature by exploiting a spatial structure via a sequence of convolution pooling layer, and then they apply some post-processing the representation using fully connected layer. And so far we saw the improvement of LeNet by AlexNet and VGGNet mainly is because they use widened and deeper network. However, networking network think a bit differently. They think about, okay, using the fully connected layer or MLP in the beginning of the neural network. The networking network composed of the name block. We first learn what is the name block. The idea behind a networking network is to apply fully connected layer at each pixel location if we have images as an input. Indeed, we apply one deconvolution for each spatial location. Here, the NIN block consists of one convolutional layer followed by two one-in-one convolutional layers that act as a per pixel fully connected layer followed by a nonlinearity or like ReLU activation function. And the convolutional window shape in the first layer is typically set by the user, and it depends the input data or input images. And also then the subsequence window shape is also fixed to one in one. Here is like the figure of the one NIM block. The NIM network composed of several NIM blocks, which can be used within the convolutional stack to and also allow us to having a more pixel linearity. And on the top, we do not have any fully connected layer after this name block, and instead we have global average pooling, which I am going to explain it in continue. And here by using this, we are somehow reducing the number of channels to desired output that we want. For example, for the fashion MNIST classification, we have only 10 class. And by removing the fully connected layer at the end, we somehow reduce the number of parameter, which is better because we have fewer parameter to be tuned. And also the NIM design influence many subsequences in a convolutional neural network design. Here is the comparison of the VGG and also NIM Also comparison of the VGG block to NIN block. Here the NIN network composed of four NIN block, and at the end of each block we have like max pooling layer, but at the end of the last NIN block we have global average pooling. And these are the references which we use in this section. Thank you for your attention.